I'm Saeid Sadeghnejad from Jena University, and today I want to present you how Python scripting can be used for Pore-Scale studies and AI modeling. My co-authors are Dr. Friedrich-Schiller-University and Thorsten Schaffer, Friedrich-Schiller and Michael Kirsten from Mainz University. There we have access to the GeoDict license, and Dr. Thorsten Schaffer from Jena University, as well as I. Today, I will talk a little bit about digital rock physics and how AI can be implemented in it. And I will show you GeoPy applications, and after it, we will see several case studies in our research that we used GeoPy for coding and using the GeoDict capabilities. First of all, our recently established group, AI and Machine Learning at Applied Geology, Jena University, we are focusing on two, as the name shows, we are focusing on two topics. First of all is Pore-Scale modeling and digital rock physics, and the second research area is data-driven solution and machine learning applications in geoscience. And based on the availability of micro-CT scanner in our lab, and also the supercomputer of Jena University that provide us both CPU and GPU nodes, and availability a lot of softwares, and top of all of them GeoDict, we have enough infrastructure to run our researches. Let's take a look at digital rock physics workflow. Digital rock physics workflow starts with sample preparation at the left side. If I can bring my mouse there, yes. And then continue by 2D, 3D imaging, and then we will go for some pre-processing steps. It can be filtration or finding the region of interest. Then we will go for segmentation task. And here we can either go for pore or solid characterization, or we can go for numerical models. Either we can use direct Pore-Scale simulation, the same as Flowdic is doing, or we can extract pore network models and do pore network analysis to predict the properties of the rock sample. But let's see how AI can help us. As Mike showed us yesterday, Mike, where are you? Ah, there. AI can help us in different sections. For example, the first application of AI can be using for increasing the resolution boosting or increasing the resolution of the images or artifact removals. Also, AI can help us for AI-based segmentation. Or we can use, as one of the other colleagues yesterday explained us, I just forgot his name, Dr. Orkun Furat from Ulm University is here. Is he here? No, maybe. We can use generative AIs for reconstruction of models. And also, we can use unsupervised clustering for pore or solid phase characterization, or we can use, for example, AI pore network model extraction methods, or at the end, we can skip all of these steps and use regression models, AI-based regression models to predict rock properties directly from the images. But what we need in GeoDict in order to do all of these tasks is Python code or Python scripted in GeoDict, which is, I think, maybe some of you has tried it before. And Python scripting is nothing just except a scripting interface that you can use all capabilities of GeoDict and control overall programming things inside the GeoDict, and you can get use of them. I try to classify applications for GeoPy in these four categories, and I will show you for each of these categories one of our case studies that we have done. GeoPy can be used at the top for repetitive tasks. if you want to do something every day, every week, every month, you want to do the same thing, it's better to go for Python scripting. And you can get rid of running every time a lot of things. The second application is customized reporting. For example, if a company wants to put the logo of the company at the top left of all of the images, the best way is not to do it each time. It's just better to go for GeoPy and create, for example, a PowerPoint result or report or Excel report with all details that he or she needs. But for some a little bit more experienced users, we can go for the next two options. For example, if we want to do some modeling or simulations which is not available in GeoDict, maybe we can use plugins or extensions. We can write our own code and couple it with GeoDict capabilities, and then at the end you can extend the capability of GeoDict to the field of your study or research. And at the end, if you want to exchange data from GeoDict to other softwares, or you want to bring from other softwares data to the GeoDict, we can write API with the help of Joe's Python codes and connect both softwares together. The first example is a very good example of a repetitive task. In this research, we try to compute the representative elementary volume of a block. And as you know better than me, the representative elementary volume, or REV, is the volume above which the Pore-Scale heterogeneities doesn't affect the bulk properties of our rock sample. And there are two approaches for computation. The first one is the deterministic approach, in which we use some nested volumes of blocks to compute the property of interest, say, for example, porosity or permeability. Or in the statistical REV, the second one on the right top, we use some blocks with variable sizes, and we try to sweep those blocks inside our whole structure to compute the property of interest. In this study, we tried two sandstone samples and one carbonate samples. We did scanning. We scanned them at Deutsche Synchrotron DESI, and we received a high-resolution image. And also, we scanned all of these three samples by lab-based CT scanners, and we received a low-resolution scan. And then we went inside the GeoDict. We computed REV for porosity, permeability, surface area, Euler number, and two integral of mean and total curvature from Minkowski functional. And we used the MATDIC module to compute the tortuosity of the system. And for this kind of calculations, we had 3 rock samples, 2 resolutions, 16 point per parameter, and 7 parameters, and it was 700 simulations. And for lazy people like myself, I can do only maximum 5 simulations, one by one, and at the end I should find another way. And the way is using GeoPy and Python scripting. Just I check it out on a small scale samples and then press the button of the macro, and then I waited, I think, I don't remember, maybe several days to receive the result of all of this calculation. This is the typical example of a repetitive task. I told you that we can use GeoPy for customized reporting. It's for generating Excel files, PowerPoints, but here I implemented something else. On the same project, if you can see here, I put all of my 7 parameters of interest in the user interface of GeoDict. It was a little bit tricky to do that, but I finally could do it, to plot it on different tabs. And I showed the mine results in the GeoDict user interface. And it's possible. So if you want to do anything with the help of GeoDict, you can do it easily. The next example is AI applications. Mike yesterday showed us some resolution boosting algorithm to increase the resolution of CT scan images. We did something similar here. We start with a low resolution scan and a high resolution scan here marked as ground truth. And I remember from yesterday, there was a question about the scanning time. I can answer it right now. The low resolution low resolution imaging, we mean a scanning of 1 to maximum 2 hours. But for high resolution imaging, if we want to go for example, 1 micrometer resolution or below, the scan may take over 20 hours. It means the saving of scanning time is something from 2 hours to 20 hours or even more. And this is the basics of these resolution boosting algorithms you can use. Here we start with low resolution algorithms. We did some bicubic interpolation of those algorithms, and we used compared three boosting algorithms and also the ground truth. If you look at the numbers, we had one rock sample. It was a Fontainebleau sandstone. We had six different structures, 40,000 2D images, 2 properties, porosity and permeability. You can see the final match of AI model. And in total, it was 168,000 2D simulations. And it took 15 days on 96 Xenon Platinum cores with the help of the GeoPy. Without GeoPy, nobody can run this number. I will quit my job if somebody tell me if you should do these simulations. The next example is writing some plugins and API for GeoDict. In one of the research of my PhD students, we wanted to focus on microporosity, unresolved microporosity during CT scanning. And by unresolved microporosity, we mean that if you look at this zoom section of my rock sample, we have some area we can with 100% say that it's a grain, it's a solid. We have some area we can say, okay, it is 100% pore, but we have some grayscale area in between. It means that we cannot say that is it either pore or grains. It's something in between. And we call this area unresolved porosity. And the reason for this kind of things inside our CT scan is that the resolution of the CT scanning was not enough to capture those areas. And we tried to, first of all, use the AI capability of GeoDict to segment it in 3 phases of grain, pores, and unresolved pores. And then we use the octree structure to replace those unresolved area with higher resolution images. It means at the end, we had a multi-resolution image in which some areas, like here, the gray ones, we had I'm not showing there, so sorry. With the green areas, it means that with the gray areas, we had some images with large voxel sizes, but we had some unresolved area showing here in green. We replaced those areas with the smaller voxels, and at the end, we had a dual voxel image. And here we decided, for some reasons, to go for pure network modeling on top of directly solving this the problem. And we wrote some API to take data from GeoDict and feed it to other softwares like OpenPNM or in this project we use OpenPNM for pure network modeling and computation of permeability and relative permeability inside the sample. This is a typical example that we can use it for data exchange between GeoDict and other softwares. The next case study that I like it too much, which was something I called it digital rock biology, with the same terminology of digital rock physics. I call it digital rock biology because some biological activities are responsible to apply some changes inside the porous media. As maybe you can see from this animation here, we had some bacteria inside the porous media. The porous media was a kind of a micromodel, glassy micromodel at high pressure temperature. And the bacteria not only can move through the sample, they can colonize somewhere and make some biomasses inside the porous media. And this project was a project between Mainz University in Germany, my former university, and 2 universities from Austria, Montana and Buku, and Bergen University from Norway. And we wanted to simulate this one. So the first step is to compute the flow field. It's so easy. We can use FlowDic for computation of the velocity field. But what about the movement of bacteria and other things inside, growing of these things? We had ADIDIC license, and we tried to use ADIDIC, but ADIDIC is not designed for this kind of simulations. Then I sent an email to Dr. Christian Hinz. Where are you, Christian? There, at the end. That gentleman helped us with a Python code of ADIDIC. That code enable us to differentiate between deposited particles and still flying particles in the porous media. And with the help of that Python code, we could differentiate these two things from each other, and then we changed those deposited particles or deposited bacteria in this case to solid voxels, and we applied our biomass growth with a kinetic model. And we put it in the loop. It means that every time we run the ADIDIC for flying of those bacteria inside the system, we update the flow field and do it again until the end of simulation. And this animation shows the speed of simulations. I wanted to do it quick to show you. I speeded it up. And the green ones are those flying bacteria, and the red ones are those deposited bacteria inside the domain. And I will play it again. If you focus on one point and look at one red area, you can see a slight growth of those red areas. It means that our bacteria are producing biomass and closing the pore spaces. We didn't stop here, and we get forward to another research with the help of that code we have developed, and we went for particle retention mechanisms at the sub-pore scale. And I think with the presentation of today morning about sub-pore scale things, here is a little bit different in our case. By sub-pore scale, we means that the size of our particles are much smaller than each voxel size. It means that we need several particles to fill a voxel size, and it makes the simulation much more difficult. So we decided to get through the Python scripting and do something very simple but very effective. Here we subdivided each voxels into smaller voxels to find the fraction of each voxel which is being occupied by our particles. Here I'm showing large particles, but the case for smaller particles are the same. We have a particle here who has been attached to the solid voxel, the green one, the white one are void voxels. And here I can compute, based on some geometrical properties, I can compute which fraction of each voxel has been occupied. For example, this voxel has been occupied 65%, but the other two 5 and 6 and 5%. It means if we have some kind of threshold in the system, for example, say 50%, now we can switch this void voxel to the solid voxel. And now we can continue the simulation. And if we update the flow field, now we have some voxels now converted to the solid one. Then we can keep our simulations continuing. And this is one of the examples here. The green one are the flying particles, and the purple one are the deposited particles. And I haven't shown any structure solid phase inside this image. As you can see, the particles can fly inside the domain. And with the help of these plugins, we could publish several papers on the mechanisms of pore plugging when we have particles inside our flow. For the same code, I had a lot of things to set. And as you can see from the top image, my code had a lot of modules, so for doing different things. But as I told you, and you may understand, I was a lazy person. And so I didn't want to get through the code every time, change some parameters, and then run it again and again. So I designed a user interface with the help of GeoPy for it. And as you can see, my user interface has a lot of sections for simulation, time steps, particle properties, particle clogging, and flow simulations. And I try to put it in user interface, and I remember from yesterday the presentation of P&G company, if I pronounce it correctly, or the name was correctly in my mind. They use the same user interfaces, and it's very easy. For example, if we want to use it, we have some users that they don't have any experience in programming. This user interface will help a lot. Or if we have a repetitive task, if we want to do it every day, then they are a very good solution. Just a bunch of code copy pasting from manual, and then just designing take only 1 day, and then you can use it forever. And it's very, very easy for to be implemented. And however, at the last slide, I have somehow the same as university, a quiz for you. I want you to guess what's happening here. Here I have some hints. I have a porous space and solid space with some particle weighting here, and I want to play the video. Up to here, everything is not too difficult. We have some particles, they are moving inside the domain. Some of them has been trapped, but what happens now? Can somebody guess? Without microphone. Yeah, why? Yeah, exactly. In this simulation, let me go to the solution. Here is a modeling of particle detachment. In subsurface, sometimes particle can get trapped, but if the boundary condition of injection is changing, for example, if we increase the injection velocity or the shear forces is increasing on the solid particles, some of those trapped particles can be detached from the solid surface and gets back to the flow. And I tried it as some hobby to write this code to check if it's possible or not. And I could show that, yes, it's possible in GeoDict, but it needs a fund to focus on it and finalize it. Thank you so much for your kind attention. The top image is the Mainz University entrance, and the below image is the Department of Applied Geology at Jena University, with a good look to the Saale River in the back of our department. Thank you so much.